Hey everybody, and welcome back to Algebra 2 Online. I want to talk today about systems of equations, and a lot of this stuff should be review from Algebra 1, and there's kind of a lot to review, so this video might be a little bit longer than normal, but it's all really important stuff. And in Algebra 2, we build on this idea of systems of two equations that you learn in Algebra 1, and we extend it to systems of three equations, and really after you've seen that, you could honestly solve systems of 4 or 5 or 6 equations. There's actually like a whole branch of mathematics called linear algebra, which is our highest level class that we teach here at Stargate. And the material in that class basically studies the extension of systems of equations in higher dimensions. And there's like a whole bunch of stuff I could say about that, but there ends up being a lot of theory, honestly, related to this when you start getting into higher dimensions. It's a huge branch of mathematics. So to do something like this, if we were going to graphically solve a system of equations, we're basically just looking for when does this thing intersect this thing. And when they do, you're going to get the x and the y point that basically simultaneously solves both equations. So maybe I'll do this one in red. So if I was going to graph that, I would get, let's see, this is minus 1, and then up to over 1, up to, over 1. So we get that. And then this other equation is in point slope. So the point is at 1, 2, so right here, and the slope is negative 1. So that would be, let's see, that's negative 1, yep, negative 1, so we get that, okay. And this is a good example. So the solution is, like I said, the intersection. So if I was going to mark it, basically there, that's the answer. This point right in here solves both of those equations at the same time, so it solves the system of them. This is an example I do because I want to sell you on how bad this is as a way to solve a system of equations. Like even in Algebra 1, the idea of it is important, but I won't tell my Algebra 1 students any more about graphically solving a system other than to show them what we're doing and then to get right into like the main algebraic ways. It's just bad because you don't really know like what that point is. It's too hard to tell in this picture. It might be something like 1.57211113, comma, I don't know, maybe 1.56211131. It could be that, and we really don't know. And a lot of times in the world, like the real solution to a system will be this crazy, messy kind of thing. So it's important to know how to do it algebraically, but also to know what we're doing. And what we're doing is we're really just trying to figure out when does this line intersect this line. And this works if this wasn't a line too. Like if we were solving a system of nonlinear equations, we would still just be wondering when does the first thing, it could be absolute value or something, like intersect a quadratic or something else. But it's all about intersection points. And so for a system of two equations, we would need, I said that wrong, sorry. A system of two unknowns requires two equations, that's what I was trying to say. And a system of three unknowns would require three equations. And this idea just continues and continues. So, if you have like x and y in the last problem, we need two equations. But if we have x, y, and z, you need three equations to solve that. And a system of like n unknowns would require n equations. You always need the two of those to equal each other in order to solve it. And the answer is always the point. So like in the last problem, it could have been this weird point right here. But it's always just either an ordered pair, so something like x, y, or a triple XYZ, or it could be like WXYZ, so on and so on and so on. It's just a point that represents the intersection of the graphs. And typically we're going to start with like lines, but we will do a few things where it's like I was saying before, like when does this absolute value thing intersect the quadratic? And you could get, 1, 2 solutions. That is possible. So if we're thinking lines, though, there are 3 cases, basically, for solutions to a system of just 2 lines. And one of them is like the first picture we already drew. So we have, I'll do this and all of them. So we could have a line, we could have another line, and we know that this is like one solution. Okay, it's one case. We could also have a line, and then we could have a line that's parallel to it. And in that case, there's no intersection, so there'd be no solution. And the last case is like you have a line, and then you have the exact same line again. And in that case, you would get infinite amount of solutions. It's not correct to say this doesn't mean the same thing as all reals. Sometimes students want to say all reals, but you have infinite amount of solutions, but if you take this point up here, this point is not a solution. So that's in the real numbers. So it's only the points on here that are the solutions. These points are answers, which is infinite amount because it's a line, but it's not all reals. So you have infinite amount of solutions, that's a case, no solution, or one solution. And so just to kind of summarize like how we solve these, you either could graph things out and try to look at the picture and figure out where they intersect, but that's a horrible idea. Never do it. The other ways are good. So it's elimination and substitution. And basically, I just want to go through examples of each of these, and that's really how we'll do them every single time. This just becomes very impractical in the real world. No one's graphing these things out to look at solutions. It's so much work. The answers might be really weird, but if you just do it with the algebra, you can get the answer very straightforward. So a substitution problem would be in one like this, and the reason it's substitution is because, you can do this with elimination too, it's fine, but it's set up really nicely for substitution because I can just solve this equation, let's say the bottom one. I could do both, but this one's easier. I can solve this equation for one variable, the y. And so if I was going to do that, I would get y equals 12x plus 1. So that's kind of that part done. And then I can substitute that into the other equation. So the y is this 12x plus 1, and I'm going to take that and literally put it in that y up there. So I got 12x plus 1, that's my substitution, and then I've got minus 2 equals 7 times x plus 2. And this new equation, so that's that step done. So this new equation, I say here, should be written in one variable, and it is. You can solve that for x now, right? So if I do that out, maybe I'll try and keep these colors aligned. We would have, let's see, 12x minus 1 equals 7x plus 14. Then we get 5x equals 15, so x is 3. that is that step done. And then we're going to substitute that solved variable back into the beginning. And you can pick, I always recommend you pick the easiest equation to find the value of the second variable. So if you know what x is, you have this equation right here that's solved for y. So I would just go and plug it into that. You know that y equals 12 times then 3 plus 1, which is 37. And so it's looking like y equals 37 and x equals 3 are the two answers, but these are the kind of problems where you can check really, really easily. So what you should do is you should take these two numbers and plug them in. They have to work for both of these equations. That's what it means to work for like a system, right? It's like you're going back here, and that point, the 337, should be a point on both lines, and solve, then in a sense, solve both of them. Now, I made these problems, so I know they work, but I'm just going to say check. Yay, it works. And so we now know that like 3,37 is basically the answer to both of them. But you shouldn't really ever be unsure if these problems are right or wrong. You might not, again, know where you made a mistake, but you should be able to figure out if it is right or wrong. So I want to do an elimination one now. The elimination problems basically should have some sort of common multiple going on. So if I see this 5x and 15x, the 15x is a common multiple of the 5. It's just 5 times 3. And so that's a situation where it's really kind of begging to be solved by elimination. If one variable was by itself, then it would be one that I would probably do with substitution, but it's easy enough to just do elimination here because you see a common multiple. So the first step I'm writing here says multiply one or both equations so that you have one variable in one equation, which is a multiple of the same variable in the other equation. So what that's going to look like, I would just do this one times 3, which would give me the 15x plus 9y equals 156. And maybe I'll just copy this over. 15x, 9y equals 54. And if you, so I guess check on that first step. Then I say add or subtract the two equations. So sometimes students get in the mind that they always subtract the equations. I don't really get that. You can subtract sometimes, but you could also add. If you had 15x and minus 15, you would definitely not want to subtract because then you wouldn't get one of these variables eliminated. In this case, you do subtract, but that is not something you always do. But if I subtract these, that would go to 0, that would go to 0, and this would go to 102. And so this is saying basically 0 equals 102. So, check. Now, this is kind of different from my instructions here because we reach something kind of weird. So, next I say solve for first variable and then substitute back in to get the second and check. This stuff is all the same that you would get basically at the end here. Solve this for one variable, substitute in, and check. The reason I'm not going to do that is because I got something that does not make sense. We know 0 doesn't equal 102. And so since these are not equal, this is basically what it means to have no solution. Really, you could almost see it up here because these two are the same exact thing, but these are different. This is basically going to affect like the y-intercept of the lines. And so it's like two lines that have the same slope, but they're different y-intercepts. So like this picture right here. That's basically what we're getting. And just so we kind of know, maybe just off to the side down here, if you had the infinite solution case, what that would look like in terms of numerically, you would get something like 2 equals 2 at the end, or maybe you would get like negative pi equals negative pi, or so on and so on. You would get something that's true. All these things are true, right? And if you got something that was true like that, then it would be the infinite solution. It basically would mean that your two lines are overlapping, and every single point on the line is a solution. So this is just one where I want to solve, and I want to talk through about which method I would use. A lot of times you won't be just told, like, this problem, solve it with elimination. You have to think about what would be best. So when I look at this problem, if I see a variable that's easy to solve for, I'm going to do substitution. If I can't, I'm going to do elimination. So right here, that y variable is easy to solve for. So I'm going to solve this for y, and then plug it in down here and solve it out for x, and then I can check. So the first equation, if I solve for y, I would get that. Then if I take that y value and I go plug it in right there, I'm going to get negative 5x plus 2 times 4x minus 12 all over 2 equals 7 over 2. This is kind of nice because they're both over 2, so you could multiply by 2, and you basically can just cancel that out. And then I'm just going to distribute that 2 in. And then combine like terms, I get negative 3x. I'm going to add the 24 over. Get 31. X is going to be negative 31 over 3. And then I need to take this and I need to substitute it back there to get y. So 4 times negative 31 over 3 minus 12 should equal y, which is negative 124 over 3. I'm going to switch the 12 to a common denominator here, so I'm going to do 36 over 3, right? And then I'm running out of room, but negative 124 minus 36 is negative 160. So that over 3 would be y. And you can check it, but I know they work. If you go take like graphing calculator or something, and you plug in these two equations up here, you will see that they actually intersect at those two x and y points. So I just wanted to summarize when we use the different forms. So graphically, I can't stress this enough, never. It is horrible. You would never probably, even thirds are going to be really hard. It's really hard to tell when something is intersecting at a third. But imagine it was like, again, way back here. Imagine it was really like that number. And it very well could be. And in the real world, it will be stuff like that. You won't get these nice integers. This kind of problem, yeah, you could tick off the y-axis all the way up to 37 and see that they intersect there, but it's still not ideal. It's going to take a while. But never do it. It's not a good way to do it. Substitution. Basically, if you can solve for a variable quickly would basically be stuff like we're going to do systems of 3 equations, and you might have an equation 7x minus 14y plus z equals 2, and I would solve for z and do substitution. Z equals 2 minus 7x plus 14y. If you can do that quickly and easily enough, then do substitution. And elimination, I would do if, honestly, it's almost easier to say if you can't solve for a variable quickly. So also looking for those common multiples with the coefficients. If you see a 5x and a 15x or something like that, that could be a good situation for elimination.